cable and arc system, which is a few weeks ago, Dr. Hazrina contact me, and I cannot say no. So I just only say yes. Then I will prepare the lectures with my junior, Muhammad Fauzi Darmawan. So I will summarize some lecture, which is also, you can download it later on from Dr. Hazrina, or maybe you can also find a similar subject on the internet available already. So hopefully we will start the discussion about the cable and arc system from the applications, how we deal with the calculation, and also how we can use the computer software to develop similar evaluation through the computer program, which may be close enough or maybe different from the result obtained from the calculations. So hear me, I'm Ali from Gajah Mada University. My background on wood, bamboo structure, steel structure, structural analysis, and also container mechanics.
Sebab yang untuk Dora ni Zarin akan jadi RA sebab dia full time. Dia kena yang memang full time. Zarin dah settle dah. Dia dah habis. So dia akan dia buat briefing aku akan jadi. So dia memang akan buat benda ni untuk sebab dia tak ada extension dah. Sebab dia dah doktor dah. So dia tengah tunggu senat. So sekarang ni dia akan jadi RE. Untuk IMAT dia tidak RE. Dia setahun-setahun tak boleh extension tau. Dia setiap progress kena tunjuk. So orang
stop sharing.
Sebab tu yang kata bukan ku mati. Ku mati.
Okay. Now you can see the slide. Here we have some example of the role of the cables. In the first one, we have bridges from Indonesia. We have some cables which is supporting, holding the deck of the bridge system, and the load coming from the vehicle transferred to the cable through the deck system, and then finally the cable will transfer those forces come to the foundation. So in these cases, we can see clearly that cable only experience tension forces, no compression at all, and also no bending. So we have here only tension member, which is cable, to transfer the load from the vehicle coming to the foundations. We can also hear maybe in the figure in the bottom right side, we have some cable supporting the roof structures, and then finally become before going to the foundation. So we can see that the cable here has to support the weight structures of the roof here, and then the weight transfer finally to the foundation to the cable system. So we can see here that it is clearly that the cable will always support the tension forces through the life surface of these structures. Okay, so I need to. Okay, in suspension bridges, as you see in these photos, which I described already, we have the main cables, and the cables is like a block coming anchored on the both ends, which is what we call anchor block. So to prevent the cable from shortening, so that's why we have only tension forces coming here. The load coming from the deck, which is transferred to the vertical hanger. So the vertical hanger will clearly make this cable going down, or maybe that we call sagging. Sagging is like vertical deflection of these cables because they are holding the forces through the vertical hanger, which is created by the vehicle load. And we are clearly seeing that this cable can only displace vertically. Now, this is not allowable to have the horizontally displacement, so only vertical one. So the cable is become this very efficient structures because it's only tension. We can reach the material come to the yield point of the cable, which is very high for steel cables. And that's why we can have very long span bridges. Now it's dominated by the suspension bridges, as you say here. So we can, if you have the bridges very long distance, then the option maybe more than 100-meter long, then the option always comes to the suspension bridges, because we can have this kind of structures supporting very efficient structure at all. So then let's come to the simple cases, which is I will show you within 2 hours from now. So we have a system of the cable supporting at both ends, A and B, hinge support. And we have the cable configuration from A to C, and also from C to D, and also from D to B. When we see the geometric of this cable system, we see here that at C and D we have the load P1 and P2 going down directions, and then we are trying to write down the imaginary line, what we call the chord, from A to B, just like a straight line. And then we assume that the inclination of this chord to the horizontal line is the angle of theta. So at the moment we will see that we will have about 4 unknown reaction forces, 2 at A and 2 at B. And we also have the tension forces of the cable AB, cable CD, and cable DB. So we have 3 tension cable forces. And we also, at the moment, we do not yet the zacking, the vertical,
topologi
YC and YD. So then in total we have
maksudnya dia akan guna
9 unknown
dia pun ada dengan statistik
variable, which is 4 reaction forces, 3 tension forces, and 2 of the zacking, YC and YD. The thing that we know here is the configuration in the horizontal axis, L1, L2, and L3, and all L. But this is the only configuration that we have. Based on our background on structural analysis, we have what we call we have the equilibrium equation, which is in X direction and Y direction. So if we are applying on A, C, D, and B, we have 4 points. And when we are applying these 2 equilibrium equation for each point, equilibrium forces in Y and X direction, then totally we have 8 equations to solving 9 unknown variables. So we're still lacking for one equation. But later on, we can also try to solving this the last one by seeing the geometric of this configuration of the cable system. Later on, we can have some example, which is very easy at the end. Here's some example configuration of the cable ACDB, the same length actually, but we see here that the weight, the point load W1, W2 from the A picture and also the B figure is different. By applying different set of the loading, then we have different kind of deformation of the structure. So that's why we have the cable is also affected, the tension of the cable from A to C, C to D, or D to B will be affected by the configuration of the loading. So as I mentioned before, usually we're lacking for the equation to solve the several unknown, then it's become indeterminate statically analysis. But when we understand the configuration of the zagging, of the deflection after the loading is applied, then it's become statically determinates. So later on, I'll show you the example. Now we have some another cases. Here the cable is experienced for distributed loading. Not the previous one is the point load, but now we have the distributed loading. So here the cable is holding at the 2 support, and if we take a look and also under the distributed load W0. So please take a look on these figures. If we take a look on small part of the cable, distance X from the support of the left side, and the length is what we call delta X, and the vertical length is delta y. And we see here the way the distributed load is equal to W0 multiplied by delta x. And then we have the resultant of the forces, which is in distance of delta x over 2. Here we have tension symbol by T with the inclination angle is theta. In the all point, we have the tension equal to T plus something, which is delta T. And also the angle become delta plus rotation is the theta plus delta theta. Through the equilibrium equation, the sigma forces to x equal to 0, sum of the sigma forces to y direction is equal to 0, and also the sigma moment at all point, it should come to 0. Then we finally come to the set of equations. These three set of equations, let's divide it by delta x, which is at the end close to 0, because we take the short finite length of this cable. And if also closing when we delta x close to 0, when delta y is also close to 0, delta theta also close to 0, and also delta t close to 0 as well. So we finally come to equation 451, 452, and 453, which is the rate of change of t cos theta with respect to x equal to 0. Rate of change t sine theta with respect to x equal to W0, and also the slope, which is deformation of y with respect to x also equal to tan theta. So these three equations can be obtained just directly from applying the equilibrium equation. Let's continue for this slide. Okay. So I will not take you in detail, but let us try and see the slope at x equal to 0, which is actually here we are starting the x. When we see the x equal to 0, then the slope should also go to 0, yeah, because it's just close to the support. And then we can get that when theta equal to 0, and then t cos theta should be equal to the horizontal forces of the cable itself, because it just straight horizontally to the direction of the support of the left side. So here we start starting from the left support. So we counting the x direction starting from the left support. And then finally, we can also get from the another parameter, another consideration, that the t sine theta equal to W0 multiplied by x. And then when we combine these two, and then we trying to divide it, the equation 4.435 and also 434, and we can eliminate the t symbol, and we have the tan theta, which is equal to, in the beginning, tan theta is equal to the slope of the cable deformation. And finally, we can sum up with this, the y equal to the equation in the 5.7. So deformation of this cable. Here is y, as you can see, y is the total, yeah? Y is the deformation of during the zagging of this cable due to the distributed loading, equal to W0 divided by 2FH multiplied by x squared. So it's become like the parabolic function. So the zagging of this cable is become parabolic one, it's not the straight one, because we have the distributed uniformly is equal to W0. So we can finally find this one, and if we can have already this one, we can going up to understand what is the T tension of the cable itself. So let's come to another one slide. So then we can come up with the solution that the FH is like the horizontal forces of the cable, because the cable have the tension, but once we can project it into Y direction and X direction. In X direction, we can have the FH, okay, the symbol. And then we have the equation that if H equal to like W0 L squared divided by 2H. This is the horizontal forces of the tension projected to horizontal axis. And then when we would like to also to understand the T as theta, which is equal to 0. So this is T cos theta is the horizontal projected of the tension force. So we can replace by this number. We can also have the T sin theta, which is the vertical direction of the tension in the cable, equal to W0x. So when we would like to have the resultant of these forces, then we just come up with this very famous calculation, which is square root of the horizontal forces plus the vertical forces by square. So this is what we call the maximum cable tension. We call TH map. So TH map means the maximum tensile cable on the system, which is actually the square root of the sum of square of horizontal forces and also the vertical forces. We come up with this equation. So finally, you can use this equation 511 to understand to evaluate the maximum of tension cable based on the uniform distributed load equal to W0. The length of this cable equal to L is the horizontal length, and H is like the vertical distance between two supports. As you mentioned here, we can see the vertical axis. So those calculations finally come to the equation 5-11. So you can understand what is the maximum table. Then finally you can design the diameter of the cable. Also, you can design the quality or maybe the strength, yield strength of the cable by using this equation. So I'll show you some example, small one. Here we have some system of the cable. AD is the support, which is horizontally no inclination about any AD, so they are straight line. B and D, we have some forces like 100 kilonewton and 80 kilonewton. And the distance from A to B, horizontal direction, B to C, C to D, you can see this one. But here you have some clue that the vertical zagging or vertical elevation of the C with respect to D equal to 10 meters. So here a cable support two concentrated load in the figure below. The question is how determine the sagging or at B. So here the question is about what is the vertical length of B with respect to the line crossing A to B. So here is the question. So we will find out later on. Let's draw the equilibrium equation. I mean the forces. We have the E because E is and D is the reaction support. For him, we have two forces X and also AY. And also from D, we have dx and also dy. Okay. So we can apply the first equilibrium equation. So let's see sigma moment at A equal to 0, because here we have only cable and hinge, no moments tolerable in the system. So the total moment in A should be equal to 0. Then we finally come to understanding that dy equal to 76 kilonewton something. And also we apply that sigma vertical forces should be equal to 0, and we have the AY equal to 103 kilonewton. The same also we can also apply the sigma D equal to moment at D equal to 0. Then finally we can also have the vertical forces of AY and also vertical forces of also DY. Then we finally get all the expression of the reactions. Here we continue. Set out to B. So we have now just eliminated another part of the cable. So we just draw only A to B. And here we drop the forces of AX and also reaction support AY. And here in the point B, we should have the cable tension, but we also project it into Y and X direction. So we have the BX and also BY forces. Yes, okay. Let's see when we combine, the sigma moment equal to B must be 0. So here we can have finally that minus AY multiplied by 2 meters, the length, the distance between A to B, plus AX multiplied by YB, which is AX equal to 80 kilonewton multiplied by the YB. So directly we can get the YB equal to 2.58 meters. So this is only from the equilibrium equation, because we can solve it actually because we already know the YC in the beginning, which is 10 meters. In the real cases, maybe we don't know yet this number. So once we give this number, then we can solve the YB. But in the real cases, no one can tell. You have to evaluate by yourself. So, but please, if you have something in mind that you can just interrupt me directly, no need to wait, okay? So we also would like to see the tension in cable at A and D. So here we have some, actually just some trying to see the maximum tension forces. So we can see we have projected forces at A1 and at X. And if we would like to see how big the tension forces, so using the calculation using this one, square root of square sum, you finally come to the point which is the maximum forces of A to B. Here A to B is around 130 kilonewton. B to C, here, for example, here the number is 43 kilonewton. DC is about 110 kilonewton something. So we can now get all those tension forces. So from A to B, B to C, C, D, they have different tension forces in the cable. So that is the short calculation of this one. Okay, I can skip the length of the cable because it's not so difficult. We can use the Pythagoras theorem. Okay, let's see another one. So here, A and D has different vertical elevation. So B and C, they have the forces 3 kilonewton and 8 kilonewton. We also have no idea about the vertical zagging at the point B. But we see here that the point C, the total length is about 4 meters. The vertical direction, or maybe the elevation is about 4 meters. Here the configuration about 2 meters from A to B, B to C is about 2 meters, also C to D is 1.5 meters. So now the question how we determine the tension of each cable segment, and also what is the dimension of H, which is the vertical elevation of the B point. So that is the question. Let's move, let's start here in the beginning. Let's see if we are taking the D forces. Here the forces is actually, D is like the tension cable just close to the support of D. Let's draw the tension forces of TCD like this one. Okay. So we have TCD as the unknown forces here. We also have the at A, we don't know yet about the reaction at Y and also X direction. But when we take a summation of the moment, bending moment at A, only TCD was coming out from the equation. So we can come to this one. TCD is, let's say the 3/5 is the horizontal direction of TCD, multiplied by the 2 meters, the length, come to the A point. TCD of multiplied by 4/5 is the vertical direction, multiplied by 2 plus 2 plus 1.5, which is equal in total 5.5 meters. So because the moment direction is different, so then we deduct by the load coming, the moment coming from the load at B, 3.2 multiplied by 2, and also the load forces from the C point coming by multiplied by 4 meters. So then we can understand that TCD, which is the tension forces, yeah, equal to 6 something kilonewton. So we already now have the TCD forces. Let's draw here is the equilibrium forces at the point C. Okay, at point C, we see here that we have the TCD forces around 6.79 kilonewton. We have here is like the load forces about 8 kilonewtons. And here we have TBC, it's like the forces, tension forces at the cable segment B to C. And we also at the moment, we do not yet what is the inclination or maybe the theta BC. So we have two equations, which is equilibrium of sum of forces at Y and also at X direction. We have two equations, we have two unknown, which is the tension forces of BC, segment BC, and also the rotation of theta BC. So using those two equilibrium equations, we can finally come up with these two unknown variables. So we can finally get that theta BC equal to 32 degree and also TBC equal to 4 kilonewton. So those two equations lead us to these two unknown equations. So we can discover this one. Again, then we come to B point. So after we come with C point and then we come to B point. And then the B point is, again, we have two unknowns, which is the tension forces segment of cable BA and also the angle of BA. We have two unknown, and then again, we apply to equilibrium equation of forces at Y and also at X direction. Then finally, we come with these two unknown variables. So we can solve it all of them. So that the question about the H. So we can, after we know the inclination of BC, and we have the horizontal distance of A to B is 2 meters. So finally, we can use the it's about sinusoidal function or maybe geometrical. We can get finally the H point. So the H is about 2 meters distance between A to B multiplied by the tangential degree of theta B to A, which is equal to 45 degree, 43.8 degree. So finally, we can come with 2.74 meter. So we come up all this problem using the structural power calculation at this moment. Here, our calculation using the SAP 2000, which is, I think, I don't know, maybe you are familiar with SAP 2000, our commercial structural analysis program. Let's see, let's compare this one. So using the computer software is depend on what kind of model, because in the computer software, you must idealize the structures, the load application, also the boundary condition of the support, and also all the point of B and C. And you have to make the weight of the structures become meshless, because in our calculation, hand calculation, we assume that the cable has no meshes at all. Actually, in the real application, it has the mesh itself. So, but sometimes, depend they are comparing with the external load, this weight of structures become small in some cases. So we can neglect this weight of the structure itself. So let's see, let's compare. I will take a look only one cable. So here, the cable from A to B, according to our hand calculation, is about 6.9 kilonewton. But in our numerical model from the SAP 2000, we come up with around 6.88 kilonewton, which is not exactly the same, but there are some errors, some different. Okay. Here, the BC segment, we have the hand calculation about 4.82 kilonewton, but our SAP 2000 give us around 4.79 kilonewton. Segment CD, our calculation is about 6.79 kilonewton. Here, the SAP give us like 6.79 kilonewton. Yes, you see there are some different. We know exactly that our hand calculation is the exact one. So our sub 2000 is depending on how you model the system of the cable, depending about your assumption about how the load is given to the system. It's not completely picture. I mean, it's not completely the same as we are doing in the hand calculation and stuff. So there will be some different. Again, you can also use another commercial software like some ETABS or maybe some ANSYS. You will see there will be small also different from our calculation with the hand calculation with the computer software. But you see, when you give some tolerance of the error, for example, 1% or maybe 5%, that could be some acceptable in the practical way. Here's some another example. I finally, when I prepare the subject, I also come to some theory which is very exciting. They stated that at any point of a cable, so I comparing these two pictures. The one is the cable, which has the point load at B, C, and D, and the elevation of the support A and E is different. So we have 4 reaction forces, we have 3 loading system point load, and also we have cable tension forces at AB, BC, CD, and also D. So the distance between A to E is about L horizontally, and vertically we can get from the L multiplied by the tangent eta. Eta is here. So we are drawing the chord, the line, imaginary line from A to E, which is here, the chord. And here is like when we take a look at portion of the cable, distance X from the A support. And here we have the elevation of the, this X point is about Z. And the distance from the cable to the chord line is equal to D, what we call Y here, the symbol. There are some important and interesting theory. They say that the product of the horizontal forces of the cable tension at X point, for example, here we have the tension is not horizontal forces, should be going along with the tensile direction, I mean the cable direction. So when we project it into horizontal axis or Y axis and multiply with the Y, which is the distance from the X, the point X to the chord, okay? So the product of this horizontal component multiplier by the distance to the chord actually is the moment. So because forces multiplied by the distance should be the moment, bending moment. And this product of the bending moment, as product of this calculation of the bending moment, must be equal to the moment which occur, assuming that it is not the cable system, it is the beam, simple beam section, simple beam structures, also having the same loading direction, P1, P2, and P3. Here, the distance of X, okay? So of course, in the simply supported system, we can have the bending moment at the point X, which is multiplication of the reaction vertical A to the distance of the X minus P1 to the distance of the X, and also minus F2 or multiplied by the distance to the X system. So they said it's the same. So let's confirm this theory whether it's okay or not. So let's see. This is some calculation. I will give you. This is the example of the theory. I don't want to become detailed, but this is the calculation in the left side about the moment A. So this is the two-in cable system. At certain X, example is also has to be equal to. This is example of the cable system. How we evaluate the moment, the moment which is product of the horizontal direction forces multiplied by the depth, by the distance to the chord system. This is the formulation. Okay, and let's see here the formulation for the simple supported system. We can finally just now to the system. Okay, so let's consider our previous example. Here we have the Y system is about in the previous is about something about 3 point something. Okay, so we have the Y axis equal to about the distance 0.373 meters. So the Y is equal to 2.74, which is we obtained previously. So here the distance is about 3. Now we have the Y here is about 2.01 meters. So let's see the component of this horizontal axis. We have see here that we have the horizontal axis about let's project it. We have here the cosine is here. We are probably, I mean, we have noticed that the theta BA is about 53.8 degree, and then we come up with the horizontal axis equal to 4.075 kilonewton. So when we multiply this horizontal axis by the distance, we come up with this 8.19 kilonewton meter, which is the bending moment, not in the cable system. It's just the product of the projected horizontal forces of the cable at point B multiplied to the distance of the cord. Then we come to this simply supported system. The same 8 kilonewton was applied at B and C. And let's come to this one. So we have the vertical axis at A equal to 4.09 kilonewton. Then the moment at point B equal to vertical axis multiplied by 2 because the distance. So it's about 8.81 kilonewton. Look here, the moment is about the same. So just to confirm you that the cable system is come to very close by the exact solution. So you can use this theory to verify your result that your tension forces is correct by using, I think you already knowledge on simply supported system. So you can do this calculation at all. So this is the trying to utilize. Another one is example of sometime in our cable stay bridges or maybe suspension bridges, we have very huge number of the vertical hangers. So not only 1 or 2 or 3, but we have maybe 100, or maybe we have 1,000, maybe we have almost maybe 10 or maybe 20 or maybe 50 numbers of the vertical hanger. So we cannot like solve easily by understanding of this point load. It's better to using like assumption that all weight is like distributed to some cable, because the cable distance is almost usually in the same interval. So the distance from one cable to another, one hanger to another hanger is the same. So at the same time, they are supporting the deck of the bridge system. So now we are assuming that the weight of the cable is just very small compared with the weight of the deck system itself. So then we can eliminate the weight of the cable, and we just now here the uniform load coming from the deck system. So when we are solving like this one, as the previously discussed, so we are now in, I want just excuse me, I'll back here to our theory in the beginning. It's just to remind you that our theory is just coming to this way. So here we have our theory to obtain the maximum tensile forces, maximum tension force on the cable, Tmax, okay, by assuming this kind of configuration. So we have like here is like the X starting from the elevation of the left support, which is lower compared with the right support. So to adapting this kind of assumption, then we have to deal with our structure here. Okay, so here we are assuming that the X is starting from the B point, because B is the lowest one. So X is starting from B. So B point has X equal to 0. and then become positive to become to the right side, and negative become to the left side. So this is our assumption. So here we have the x prime for the left side, the total from B to C, and from B to A, it should be 330 meters, which is the total length from A to C minus with x prime. So this is our assumption. So finally, we can treat this one as what we have done in formula derivation, okay? Formulation derivation. So here we have x equal to this number. We have a 6 meter as the h, yeah, the symbol of h. We have the h here. We have the way distributed loaded equal to 12 kilonewton per meters. If horizontally, Fh is equal to the forces at horizontal at point B, as we remind earlier. So using this equation, finally we can see that x prime equal to 4.3 meters. This is the x1, x prime, okay? So the fx, which is the horizontal forces at point B, equal to 1 multiplied by x prime squared. So it's become parabolic function. Okay, parabolic function as we previously derived from the assumption and the calculation. Okay, so we already have the distance, we already have the xy, the x prime, and also we have the h, which is equal to 6 meters. Then we finally we can come to the tension forces. So here we can come the tension forces at the cable at point A to B equal to this number. So here the theta A is equal to the 261 kilonewton for the tension forces. So just come to our previous theory, which is maybe, I don't know, maybe Dr. Hazina will describe later on about how this calculation, but actually those are coming from our previous derivation. So we can have the tension forces from A to B equal to 281 kilonewton. And also we can have at point C, here we have the tension force equal to 201.5 kilonewton, and here tension from at the point B, which is equal to 145 kilonewton. So 44 kilonewton. So we finally come to the solution. We already know the tension forces at every segment of this cable system. Okay, I think this is the same. Yeah. Then our sub 2000. Let's see, let's compare our calculation. In our previous calculation, TC equal to 201.5 kilonewton in our calculation. But here in our sub 2000, we are coming with 200. So it's quite big difference, okay? Here we have in our calculation at B, point B, around 154 kilonewton, but here we have 151 kilonewton. At TA, we have around 261 kilonewton from our height calculation, but here we have 244 kilonewton. So quite different. So here we our model assuming that this is frame element, but maybe later on you can use the model not a frame element, but it should be cable element. So some computer software also able to model the tension element, but some software cannot. So they have to use another element system like frame or maybe truss element and so on. So there will be some different from the model, also from the hand calculation, but to be true that our hand calculation is the right one at the moment, because it's simple one and we are defining based on our hand calculation and all are exact. But not all structure could be solved by hand calculation. For complex structures, we cannot do with using the hand calculation at all. So we need to rely on some computer software. But please remind that there are some possibility error or maybe different between the exact solution. So I think this is the end of the subject on cable system. I have some homework for you. Just, I don't know, you can send to me or maybe send to Dr. Hazina or Dr. Safarina to check whether your calculation is right or maybe It's not.
Yes,
Yes, yeah.
good one, Dr. Ali, good one. So all
Yeah.
students, you guys need to do the homework, okay? And then you can look into this as well for your understanding for the preparation for your assignment. And what Dr. Ali has shown here, which is comparison with the sub 2000 software, is very good because your assignment is something you have to do some like this, meaning that you have to do with the manual calculations and then you need to verify it by using the software. Okay, Dr. Ali, continue.
Okay, may I have some water, please? Okay, I take some water for my refreshment, Dr. Alfrina.
Okay, sure.
If your student have some questions,
Yeah.
some
Do you have any questions from students? Come on. So far, do you have any questions? Anyone? Please ask questions. If you have any about the software, about how to about the theory, you can ask the questions. You can interrupt and ask the
Yeah.
questions to Dr. Ali. Don't be shy, okay? Anyone?
Oh,
Can you hear me?
yes,
Oh yes, I'm
absolutely.
Kawi.
Yeah.
Good. Yep.
I want to ask you what is the best software other than SAP 2000 that easy to learn?
Easy to learn. So most of my students utilize the ETABS. ETABS is also ETABS is I don't know the software so many. We have ETABS, we have ANSYS, we have another software which called I don't know. This is maybe two famous one, the ETABS and SAP 2000 and also ANSYS. But for undergrad student, most of my students utilize SAP 2000. Most of my students. But for postgraduate student, my student usually utilize the ANSYS and also ETABS. Those are my students usually to analyze the building, also the bridges. So, but for undergraduate, because you are learning with the internal forces, so sometimes you are student neglecting the deformation about the strain deformation, also stress contour and so on. You focusing on internal forces like bending, shear, and also the axial compression or multi-axial tension. So I think SAP 2000 is quite well and everyone using this one. So I suggest that is the best SAP 2000 for you during during undergrad student. That's my understanding. Thank you.
Yeah, and I would like to add some more. Kawi, a very good question from you. Okay, there are many software, just like what Dr. Ali said. Another one is that the Stat Pro also can be used. Stat Pro, but Sub 2000 is the most easiest, the more user friendly, I guess, to be used by the undergraduate students. Okay, any more questions?
Can you hear me?
Oh, please, Pak Rizal, please.
I have a question regards about the software. Is the software freely access on the internet, or do I have to subscribe to like some kind of plan that I have to pay like a monthly pay to use the software?
Oh, here in EGM we are member of officially it usually is like a sub 2000. So all students can use this computer, but they have to use the computer at campus because it's not personal one. So, but just to my understanding, sub 2000 also have the student version, which is free. So student version is just the short version, which is limit on, we have some limitation on the number of the nodes, number of the element. So maybe they can be two-dimensional model or maybe three-dimensional model. They are free, but they are limit the number of the node or the members. So you can apply for the student version, which is free of charge. But for more complex model, you have to come to a computer system at campus. but you can also use remotely usually. Here in GGM, maybe quite similar with the same rule regulation in UITM. I don't know, Dr. Azrina. Okay, that's my comment. I hope answer the question.
Okay, thank you.
Okay, so please do this homework. I think you can like start from the, I mean, try to release the support of F here, and then you I mean project it to the forces F to X direction, to Y direction, and then you start calculation getting, and then after that you are starting from F to E, E to D, to C, to B, to understanding the table tension, and also the inclination from the horizontal axis. So it's just the same. And then the interesting how you model this one in the computer software, because you need to have some assumption on how we behave this point B, C, D, E in the model, because it's not easy. And also we have to assume that this kind to be cable element, which is no need. This is only vertical axis, vertical deformation only. We not allow this point B, C, D, and A to have the horizontal displacement, only vertical one. So you have to check the model again and again to verify. And later on, you can try to practice with the theory that the product of the horizontal axis of the cables tension to the length, I mean to the distance to the cord, should be equal to the bending moment when it is simply supported system metal. So please exercise with this one. I think I found this theory is quite interesting at the end, not in the beginning of the calculation, but it just to verify whether your cable tension calculated is right or not. So I will continue on arch structures. I think later on. So please, okay, please.
I want to ask you about cable structure.
Yeah, okay.
How do factors like cable and tension influence the overall stability and efficiency of the structure?
Oh, okay. Yeah. Cable in many literature is always said that the cable system is the efficient one, because in cable we only have the tension forces at all. We only have the tension forces. We don't have shear forces. We don't have the compression forces. We don't have the bending moment. So we use all the cross section of the cable multiplied by the yield strength of this cable. It becomes the tension capacity of this cable. So that's why it is very efficient, because in many cases, the highest properties, mechanical properties of our metal is the tension one. When you compare with wood, you have the tension strength is much higher compared with the compression strength. When you compare with the steel under the tension could reach the yield strength, but under compression they can easily get buckling. Also in another like beam member, when you have the beam, you have the bending moment, and this bending moment become initiating the crack or maybe the tension in the lower side, but compression in the upper side. It is lower compared with we have the uniform tension forces. So this is very efficient system of structure of the cable. So, but please do please consider that the fracture of this system is just suddenly. It's just suddenly. Once they reach the yield strength, suddenly propagate and suddenly collapse. Just to understand this one. So it is very efficient structure, but when it comes to the collapse, it's become very brittle. That's my understanding. Afif, is that answer your question?
Yes, doctor. Thank you.
Okay. So if no more question, I'll come up with the arch structure, which is more also complicated as well. So here are structures which always been nice photos. So some I think the right side is the London Bridge. I don't know, probably Dr. Hasina, can you confirm this one? Dr.
Yes,
Hasina has
correct.
been long in
Yes.
UK, I guess. I went there for a while for vacation, so I found that okay, the horizontal bridges. I mean, the deck can be going up or down depending on the ship coming through this reef. I mean, the bridge. So it's quite nice. So here in the left side we have the arch system, which help the transporting the vehicle load on the top going to the foundation. So we have the vertical member here is like transferring the load from the deck coming to the arch system and then from the arch going to the foundation. So this is kind of also another efficient structure as well. We will see in these cases that the arch system here will completely experience compression member in contrast with the cable system. Cable system experience the tension member, tension forces, but here in arch system, the structure will support the compression member. So I don't know, maybe Dr. Hazrina already in mind that these two structures has to be in one subject because they are contradictory to each other, but they are efficient at all. So here the support, another case of another bridges, which is very beautiful, and they have the arch in the bottom side, bottom structures. So these arches will transfer the load from the top to the foundation. So usually in the bottom, like fixed arch, so their support is like fixed, which means they can resist the axial forces, shear forces, and also the moment forces. So this is indeterminate statistical analysis. So we cannot do it at the moment. Here another one is like two hinge system. So the support is here is the hinge, two hinge arch, commonly made from the timbers metal structures, steel, or also from the timber. It's also we have statically indeterminate because we have 4 unknown reaction, two from the left support and 2 from the right support. But I think you are now just already have 3 equations: sigma moment equal to 0, sigma forces at y and x direction equal to 0. So you have only 3 equations, but here you have 4 unknowns. It is not also it is also indeterminate statically structures. But also here we have the 3 hinge arches. We have another hinge at the top, at the crown here. So this is become statically determinate because you have another one additional equation of equilibrium, which is sigma moment at point C must be equal to 0. So you have 4 equations, you have 4 unknown reaction. So here in the right side, this is statically determinate structure. So I'll try to cover the subject, the 3 hinge arch and also the 2 hinge arch. Okay, for the left side fixed arch, maybe you can learn later on when you have more time. I mean, after maybe you increase, I mean, you're going to another level of in your study. Okay. Okay, so here we have 3 hinge arch structures. In the top, we initially installed the hinge system. It's like we have for example, if you have the steel member, so assuming that this arch constructed from the steel structures, so you can easily just make at the top it taper 1, so the cross section is not straight, but it's become taper, and those 2 have the big hole, and you put the dowel just to connect, and this dowel can resist the vertical forces, can resist the horizontal forces, but they are allowed to have the rotation. So it's become the hinge. So that's why we call 3 hinge structures, arch structures. So we can just coming out to this free body diagram at the left side and the right side. So you have now using the 4 equation equilibrium, we can solve the reaction at point A or also the forces at point C. We have 4 unknown reaction, and finally you can solve it by using 4 equation of equilibrium as I mentioned you before. Also the same in the right side. So it's become statically determinate now. Here is just what I summarized in my talk. Just we have 4 unknown reaction at A and B total. We have the 3 equation of the equilibrium, as you already know. Sigma forces at y and also at x here horizontally equal to 0, and also sigma moment at any point it must be equal to 0. But now you have additional at moment at point sigma moment, or maybe sorry, it's moment at point C. It's not sigma. I am sorry, I need to remove this one. So it should be not sigma moment, but moment at hinge at point C must equal to 0. So please, Dr. Hasina, in my slide later on, help me on removing this sigma moment at mh equal to 0. It should be only mh equal to 0 without summation symbol. Okay, I hope you understand.
Sure, Dr. Ali.
Yeah, thank you so much. Here, example. So an arc divide, geometric equal to the parabolic function. Here is equal to y. This is the vertical elevation at the point at the crown equal to -10/20 square multiplied by x squared. So you have the parabolic function. Here x at point B equal to 0. So we start from x at the crown here. So the question is about 3-hinge open spanner back arch bridge like the one shown in the photos has a parabolic shape. If this arch were to support a uniform load and have the dimensions shown in the figure, so the uniform load is 8 kilonewton per meter. So the arch is subject only to axial compression at any intermediate point, such point, for example, here. Okay, we will try to demonstrate that all forces are actually in the compression, inertial forces. So we have no tension forces here. So we need to prove here just in any point here, for example, point D. Let's calculate this kind of forces here. Okay, let's see. We start our calculation. So here, applying the free body diagram. So here we have the uniform load in total. From in the beginning we have 30. Sorry, in the beginning we have 8 kilonewton. Multiply by 40 meters length. So we will have 300 kilonewton, 320 kilonewton at the top because it's the symmetrical. So I just put in the load level. So rather than we are, so we have the resultant and we take the moment to the distance to the point A. So we see sigma moment equal to 0. Of course, because it is pin support AP, we need to say sigma moment because it is pin. So moment at A equal to 0 because it's spin support. So then we come up with the calculation. Here the equilibrium equation, then we have the C1, the reaction of point C vertically, which is equal to 160 kilonewton. 60 kilonewton. It is clear in mind that symmetrical one, so these vertical forces must be shared together equally at point A at point C. So actually we can just simply say that vertical reaction of AY and also C1 must be equal, and they are equal to 160 kilonewton. Okay, then let's see the half side. B is actually the moment, is it the pin, the hinge that we have in the crown. So moment at B must be equal to 0 because it's pin, is the hinge. Let's take the all bending moment with respect to point B equal to 0. So we have the point reaction Cy vertically multiplied by the distance. We have the reaction of Cx multiplied the distance to the point B, and also the external load. Then we finally come to the horizontal forces at point C, which is Cx equal to 160 kilonewton, according to our assumption, which is coming from the left direction. Again, so here we have see that By is equal to 0 because the vertical axis is 160, and here we 160, so we have no vertical axis at point B1. So here we can have the By equal to 0, Bx equal to Cx, because it has to be equal horizontally forces. So another, we have 160 kilonewton at Bx going to the right direction. So we have all these reaction forces at one hand. Okay, so now we are coming to the D point. At D point, we have only at the moment D is about 10 meters from horizontally from point B, but we need also to understand the vertical direct elevation of point D to the horizontal axis. So here we take the slope coming from the parabolic function. We take the slope at the point D, which is at 10 meter distance from the B. We can see that is the tangent theta equal to minus 26.6 degrees. So here is the tangent of at the point D. Because when we would like to draw the axial forces or maybe the shear forces, they have to be at the cross section. So the normal forces is like parallel to the cross section of the and the shear must be perpendicular to the cross section. So we need, so every cross section they have different forces. It's not only one, because here the inclination will be different from one section to another section. So the normal forces also different from each point depending on the direction of the cross section itself. So when we come to point D, I will show you in more detail. Here the point D. So here we are drawing the normal forces, assuming to be compressions. Here the shear forces, and here the moment at point D. Okay. So here we have the forces at point B equal to horizontally 160 kilonewton. The vertical one is equal to 0. And here we have the 60 kilonewton, 80 kilonewton, which is half of the quarter, so it's quarter length of the arch span length. Okay. Then we using the same things. Vertically has to be balanced because for the equilibrium, vertical forces, or also here the horizontal forces, and also moment at point summation of point D. It's not moment D what we are looking, but here's the summation of the moment D must be equal to 0 at any point. Actually, it should be equal to 0, but D is not the pin or the hinge. Then the summation must be equal to 0. One we obtain here, then we finally come to that the normal force is equal to 78.9 kilonewton. According to assumption of our direction, is to be normal forces. So here we agree that now at point D having the normal forces at around this number. You may check another point, not only point D, for example, just left side to another D or point D, or right side from the point D. At every point of this arc system has to be normal compression member, compression forces as axis. This is the best of utilizing. So, for example, if you have the concrete arch system or maybe stone, long time ago, our ancestor or maybe our history demonstrating that the use of the stone as the arch bridges, because stone has very high compressive strength but low tensile strength. So that's why in this arch system we only have the problem on compression member, compression process. So that's why using the stone or maybe steel is also should be okay, but you have to worry about the buckling. But using concrete here or maybe stone material, it should be the good example because all part of the arch system are in compression system. Okay, this is the idea. Here our calculation coming from sub 2000. Our at point D, we mentioned that the force is equal to 178.9, but here at point D is about, yeah, here 170 kilonewton, another one 188 kilonewton. So you can just interpolating maybe in between. So yeah, it's just quite close because we can see maybe the average from these two numbers quite close with the 180.9 kilonewton. So this is a calculation coming from the sub 2000 and quite close with our hand calculation. So yeah, please remind that the hand calculation is the exact values. Okay, our numerical is the approximation of from our exact solution. So that is for the arch. And let me give some further discussion about two hinge arch. It is not easy. It is indeterminate structure, but for those people who are like mathematics, I think you like this one because it is more challenging compared with the previous one. And most of structure are actually two hinge structures. It's not three hinge one, because three hinge in the construction, in the application is not so easy. So people prepare with two hinge arch system. Of course, we have some more understanding about this behavior because we have four reaction of coming from the support A and B, and then we have only three equilibrium equation, sigma of forces to x and y direction equal to 0, and sigma moment equal to 0 at any point. But we have four unknowns, so we need one more equation to solve this problem. Dr. Harsina, is it okay if I give you some another to your student, another challenging? But I will briefly discuss, not in detail. Later on, they can do by themselves actually, because I like mathematics, so I think this is very, very challenging one. So when we are having this kind of structure, I just try to isolate it, part of this arc structure. So this one actually coming from the complete one, but I try to cut it down, and all this has to be balanced, has to be stable if it is in good calculation. So I try to take some small part of this arc system, which is the length of ds. Okay, here we have support from like for example horizontally forces, also vertically one. And at another one, we have the combination of the shear force, moment forces, and also normal forces. And here we have the external load, P1 and P2. We have to have this is to be in balance, how we want to have this one. So here, I will try to evaluate the internal energy in the member system, in the arc system. This is the energy coming from moment is the bending moment forces. In small portion of ds, this is the energy coming from the bending, and this is the energy coming from the normal forces. So we neglect this energy coming from the shear forces. So m is the bending moment, n is normal forces, E is equal to Young modulus, I is equal to second moment of inertia, A is equal to the the cross-section area. So we are sum up. Those is total energy coming from the internal forces. So those is the internal energy. And then, can you see this figure in the bottom, Dr. Hasrina? I make small illustration. I hope your student can understand. Have small ball in the curve system, and another one is the ball in the top of the curve, and another one is the ball in the straight line. You will see here that the stable one is the one in the left side. So because the ball, when they are interrupt and then going up, they will just finally going down again to their position, okay, to initial position. In case of the second figure, when you give some small forces, and they will going down and they will be going away in many places. Here also in the outermost right figure, when you hit the ball and they are going to be, and also maybe going to be, they will never return. But in case of the left figure, they will come to initial panel, they will return to initial position. This is what we call stable. So when you see here stable, they have the minimum potential energy. So usually the potential energy will be minimum. So minimum, maximum, usually we will come to the differentiation formulation. So when you have the maximum values or minimum values, you will see that those minimum energy potential has to be 0. So we apply this one because the energy is also part of the bending moment, part of the normal forces. So I use the partial differential equation of total energy with respect to h, because we want to have the horizontal forces is chosen as redundant, has to be equal to 0. So using this one, finally we can solve and we can get the h forces. What is the h? H is the horizontal forces. So once you get the horizontal forces, so the unknown reaction is become 3. So 2 reaction for another support and only vertical forces at the another support. So you have 3 unknown variable. You can solve it with the 3 equilibrium equation as you already know before. So this is the additional knowledge that you have to come. You have to sum up all the strain energy and you do some partial differential equation to get the H forces, and then you can solve all of this. So here also another like software, another things come to mind. Here we have 2 arc system. Another solution actually, yeah, another solution, because here when you're solving this one, you have to understand the bending moment at any point. You have to formulate one. You also have to formulate the normal forces. How you calculate this one? Okay, now we have to write down the formulation of the bending moment and also the formulation of the normal forces. So let's see this one, okay? Let's see to be the crown, the original of the coordinate axis. Okay, this is, we call H is the vertical elevation of the crown. If we see a point, the point have the inclination of theta with respect to horizontal axis. And here we have Y is like the distance from this point that we are considered to the horizontal axis. And this one is should be Y bar is equal to H minus Y. And here we have direction vertical at point A, at point B, and here horizontal axis at point A and point B must be equal at the moment because we have only vertical axis. We have no horizontal axis, horizontal forces. So we are assuming that this H must be equal from the A to also B side. Okay. So assuming that B is the role, assuming one, we apply P1 and P2, and there will be some significant displacement. So B will displace to B action because it is roll support. Okay, so let's calculate the bending moment of the simple beam. We call M0 and also N0, which is the normal forces at a compression should be, or normal forces at point subball by N. At any point, we can do some calculation or maybe some formulation. We can do, for example, we can do the point, for example, point C is just vertical forces multiplied by the length minus the P1 minus multiplied by the distance. That is the moment at point C. From the moment, we can see the horizontal forces at the moment when A equals 0. So this is formulation of the bending moment and the normal forces based on the assumption that is simply supported. We call N0 and also N0. Easy because you already have the structural analysis for this one. Okay. Okay, next one. So now we are assuming that we have the force of H, which try to restore the point B action to point B. So they are going down. They will move the roller from point B to point B action to point B. We need to know what is the force of H that can remove, can restore, can restore the position of B action to B1. So this is thing that we need to know at the moment. So because by doing this one, so then this structure will become the same to the two hinge structure, because at the end the B action will come to B and delta will vanish, will not be appear anymore. So this is the assumption. So we are applying for H forces. Then we need to find out. We don't care much about the delta, the number, the distance of point B to B action. We don't have in mind, but we want to know what is the forces of H that could restore point B to B action, from B action to B. So that's why finally we will come to our initial structure, which is to arc system. So this is the formulation for making the M and H moment bending at any point. M0 is about the simple beam moment. N0 is the normal forces from the simple structure, which is hinge and roller support. So we have this one. Put in the calculation. Do some small hand of the derivation on, and finally we can come for this one. And for the structure which is uniform cross section, E and I is the same, so we can just eliminate. So then come to this equation. So finally we can finding out what is the forces of H here, which is the horizontal reaction at the support of the two hinge structure using this kind of equation. Okay, so after you got H, horizontal forces at direction A and B, you can solve it because you now only have three unknown reaction. You already have three equilibrium equation, so you can sum up this equation. Okay, this is example. This is example calculation. I will not talk in detail, but you will see that here we have the load 40 kilonewton at distance of 8 meters from the point A. Here the cross one has the 15 meters of the elevation, and here the point load also we need to calculate what is the theta c through some geometric or maybe trigonometric lecture. You can have this one because it's just only tangent to the the vertical distance with the horizontal axis. You can have this one. Okay, calculate the reaction of the arch and draw the bending moment. Here are the question. Okay, let's continue. Okay, yeah, from the equilibrium we can have the vertical reaction is about 929.3 kilonewton going up to directions, and that's why we have also the reaction vertical at B 10.67 kilonewton. So here maybe we need to close it down. There are some space, actually no need to have some space. Okay, we are now formulating the Y here. We have the tan theta here. So we have the theta here is equal to around 62.18 degree. So now we are calculating the H using this equation. We now formulating the My equation. This is the moment. Okay, the moment according to simply supported from 0 to, because the bending moment from here to here will be different from here to here. So the formulation will be different. So here we are trying to segment down. So we have two variations. So we have from 0 to theta c and also from theta c to phi, which is equal to 180 degree, which is half of the total arch. Okay, this is the formulation based on simply supported assumption. Then here the formulations, complete one. So from the 0 to theta C and from theta C to phi. So it's the complete bending moment of the all arcs from the 0 to 180 degree. Okay, we have this one. And here we have the also the same totals. We have this one, and then finally we come up with the solution because we according to the formula that we defined before. We have finally have the H forces equal to 90.90 kilonewton according to the assumption of the H direction. So it will be like this one, okay? This one. We have already, so we have all the reaction of the point A and also all the reaction at point B. Then we can draw any reaction at the point, at the any bending moment, any compression member at any point using the similar or maybe the normal equation just before. Okay, so let's see the drawings like this one. Sorry, okay, like this one. This is the bending moment. So maybe later on from the bending moment, then you can also have the shear force and also have the about also the normal forces. So using equation 9 and 8, we can draw the bending moment at any point. Neglect angle can be computed, okay? So like this one. This is the bending moment. Okay, this is, I think, homework. But the homework is not the 2-inch arch because it's a bit complicated, but I don't know, probably Dr. Hasna will further elaborate and also maybe further give the assignment that we could check also together. So here is the 3-hinge. So you can apply that the bending moment at point A and point C and also point B must equal to 0. And also you have the sigma forces at all points at Y and also X direction should be equal to 0. Then you can also get the reaction of the point A and also point B, which is vertically or also horizontally. I think that's the things that I can deliver to you. For further reading, please go to these books. This is very convenient, but I guess now many students doesn't like textbook. They like to do browsing in the internet, and then finally they can also get knowledge. I think I like to hand over to Dr. Hazrina or Dr. Safarina just in case some students are really want to do some subject on math calculation. Please, Dr. Hazrina, the time I hand over to you.
Okay, all right, very interesting, Dr. Ali, for the lecture. It was good. So, and here are the readings, RC Hibler and the structure and stress analysis book. Okay, so before we end the sessions, I would like to open for questions to the students. Anyone? Students, do you have any questions? And from this, you have 2 homeworks to do. So that is very good for your preparations for your assignment. Okay, so any questions from the students?
Yeah, students usually not have question, but when try at home by their own, it's not so easy. it needs some exercise anyway.
Okay, yes. For the 2 homeworks where you have the you need to spend like probably a day or 2 to try and understand the concepts given by Dr. Ali. But for now, I can open a question for students. If you have anything to ask related to the lecture previously, anything regarding with the cable arch that you might want to ask, anyone?
Hello.
No questions? Oh, okay, all right. Ain has a question. Okay, yes, please.
Badrina, Nazira here.
Oh, okay, Nazira. Okay, one of the good students, Dr. Ali. Okay, come. Ask the
Okay.
questions.
No, no.
If you
Okay.
could also on cam, that would be nice.
Yeah, Nazira, can you turn on your camera?
Oh, impossible. Impossible. If no, it's
I'm shy.
okay.
I'm shy.
It's okay. It's
Are you
okay.
shy? It's okay. You can ask questions.
Okay. Since we've been focusing on parabolic arches, I've been thinking about how circular arches fit into the picture. I remember learning a bit about them during my diploma, but I really like to understand if their calculation follow the same general process or if there are key differences should be aware of.
Please slow down.
Oh, is it too fast?
Yeah,
You're
I
too
cannot
fast,
get the
Ain.
point.
You're
Yeah,
too
please.
fast,
Okay.
Nazira.
Okay, okay. Yeah, since we've been focusing on parabolic arches, I've been thinking about how circular arches fit into the picture. I remember learning a bit about them during my diploma, but I really like to understand if their calculation follow the same general process or if there are key differences should be aware of.
Oh, okay. Here we have the circular in our example. We have the circular one. Okay. Circular one. So I just try to get the point. If it is not the circular one, okay, are they using the same similar process? That is the point, yeah. It may be the elliptical shape or maybe another not circular one, okay, not okay. This kind of formulation is still applicable no matter the curve is a circle or not. It is still the same, the formulation of finding the horizontal forces of H. It's still the same. The things that maybe not so easy when you are formulating the bending moment M and also the normal forces N. Maybe it's not so easy when you are developing. When you are develop, I mean, they determine the derivation of, I mean, formulation, the function of moment, the function of normal forces. That may be not so easy. But the formulation, this formula remain the same. Remind this is so again. Sorry, this is again. Sorry, here. Okay, okay. Wait a moment. Why? Oh, sorry. I missed my. Okay, Wait a moment. Okay, this one. Yeah, the formulation is the same. The formulation is the same. It's just not so easy when you are determining the function of M in the equation. One, the curve is not maybe circular, maybe not the, we can also have the circular one, but maybe the theta is not from the 0 to 130, 180. Maybe, for example, you have elevation of the arch support from the left to the right side is different. Maybe then the angle will be different. It's not 180, maybe 150 or maybe something. The formulation is still the same. It's just, I mean, the equation is still the same, but maybe you have some difficulties on formulation of the bending moment here. It's good. If you want to have, maybe I can ask Dr. Hasrina to create the problems where we don't have parts completely circular one. Maybe another one, Dr. Hasrina, please. But maybe the difficulties on deployment, derivation, I mean, formulation of the bending moment itself. It's not so easy. Okay, that is my response to the question. I hope that's the
Okay.
point that you are going to ask.
Okay.
All right.
Thank you.
Okay. Thank you, Dr. Ali. Yeah, because previously they have learned during diploma for this particular course, and then as a prerequisite during the structure analysis in degree, they still have these courses. So
Okay.
that's why they wanted to know whether there are any difference. But anyway, the basic fundamentals are the same. It's just that in terms of the structure itself, the comparisons of the structures, there may be a different typical arch, parabolic arch, semicircular arch. So they have a different kind of arch, but the concepts in evaluating it will be the same. Okay. So all students, I hope you can understand that.
Yeah, so this formulation, no matter of the arch shape, it should be applicable. It must be applicable, but formulation of the bending moment at all the arc should be different because depending on the shape of the arc itself. Yeah, that will be more challenging. Maybe another homework.
They will have it basically.
Okay, thanks for the question.
So we'll give in a 1 week for softer assignment.
Yeah, for those who like mathematics, I think it's challenging. For those who don't like mathematics, it's just
They should learn mathematics.
painful. Okay, that's all.
Physics and engineering. So mathematics is the key in the engineering.
Yeah.
Okay, all right. So thank you very much, Dr. Ali. I
Yeah.
just would like to see, is there anyone to have asked any questions before we end the session for today? Just double check
Dr. Ali,
if we miss any.
Dr. Ali,
Anyone?
Okay,
Oh,
okay,
okay,
that was
okay, there are
clear.
questions. You are famous now, Dr. Ali.
Yeah.
my
Okay.
name is Adam.
Okay,
I
please.
want to ask about the theory. Why the
Okay.
arches is more suitable for carrying compressive force than tensile force?
Oh. Okay. This is maybe my. Okay, I'll start this one. Okay. Okay, just one moment. Okay. Okay. I have this one. Moment. Wait a moment. Okay, I'll come to this one. Okay. If we see here the arch model system, here at the support they have the fixed support, and then usually the load is in the top going to down direction. So the load will coming from the top, and they are trying to push this arch. For example, arch is at the beginning there this kind of curve, but once we put the load, external load, maybe there will some like this one. Okay, maybe some, I don't know. Can we just let me pointer? Maybe pointer I will change into line. Okay, okay. Can you see the red one, the red line that I mentioned?
Yes.
Okay. So in the beginning, we have the line of the arch like this one. Sorry, it's not so easy to. Okay, circular one. But one we have the compression, then it become like this one. Usually wrap in the top, maybe just going down. So significant deformation and the crown. Okay. So the post is trying to push. We are transfer the load from the top to the foundation. This is the basic initial one. So I would just clarify my postdoc. Actually, we mostly dominated by the some normal, normal, which is compression member. But here we have some bending moment. As you mentioned, as we saw earlier, we draw the bending moment. The bending moment, here we have the, for example, if I cutting down this one, I'll see this is the cross section of the arch we are mentioning. We have the normal forces, which is always compression mostly, but we also have the bending moment. Bending moment usually in this kind of, thing I need to have some. Can I draw a little bit in the here, because maybe I draw here. So I will show you the again. This is the part of the arch system. We have the compression member here. Okay. Maybe in this part, in this point, we have the bending moment as well. So this is the bending moment. This is the bending moment. Oh, yeah. The bending moment here. Okay, the bending moment here. So the bending moment will have some combination of tension and compression. Okay, it is normal. We understand this one. So then we will sum up. So we sum up the bending moment, which is combination of tension and compression, and we have the compression. So I'm quite sure that at the end, the final one would be like this one. The final one we combine is all will be in compression, but maybe not in the same magnitude. So when we combine, okay. So this is the combination of bending and the normal forces become all normal forces, but all in compression member. So we can have even this arch structure have the bending moment, which is normally combination of tension and compression in the different upper side or maybe down lower side. But when we combine with the normal forces, we can guarantee that all cross-section of the arch system will be in the compression member. Then maybe we need to verify. I don't know, maybe Adam, if you could help me. Here, we could help me. Okay, we have this one. Okay, we have this one already drawn. Okay. Here the bending moment. Sorry. Okay. Sorry, this is the last one. Okay. Okay, here I saw. Okay, now if you have some time, Ada, please help me. We have the bending moment here, and please also draw the normal forces along all the circular arch, and then do application on summation of each bending moment with the normal forces. But maybe you need to design the cross section because you have to do some Young modulus. You have to understand about the second moment of inertia. But then I can guarantee that when you combine the bending moment plus with the normal forces, then all the cross section will be finally in the compression member. That is my response to your question, Adam. Thank you.
Okay, okay. Thank you for the explanation.
Okay. This question before we can begin the lecture. There's no question. Our session. Okay, so I need to everyone is turn on the camera. Stop. All right. So please everyone.
Okay, first of all, we would like to say thank you very much for our honorable speaker for today.
You're welcome.
Please give your big applause to Dr. Ali, everyone. But we cannot hear, but everyone, can you give your big applause? Okay, good.
Yeah.
Thank you. So this topic is very important. This topic is very important because of your assignment. Okay, so now can everyone please turn on your camera for us to take a photo session. Everyone, please. Nick, Nur Aisyah, Nurul Irwani, Husna.
Please turn on your camera.
Yeah, your students are too shy to have the photos with us. It's okay, it's okay. We have here some of them, yeah. Yeah, hope to see you in July, Dr. Hazra, Dr. Rina. And
Yes,
I will kidnap you to Putrajaya, yeah? You have to go.
Okay, sure. Let me know when. So we will go together to Putrajaya.
Yeah.
Okay.
Yeah, thank you.
I will take them on.
Okay, come on, everyone, please. Okay, another one.
Okay, so
All
By
right,
the way,
I
Dr.
think
Hazrina,
we
usually
are already at the end of the sessions. So
Yeah.
thank you very much, Dr. Ali.
Welcome.
So the students, the questions on the assignment will be given soon. Okay. All right. So thank you very much.
Welcome. Yeah, thank you.
Okay.
May I? Okay, I will leave. Yeah. See, take care, both
Okay.
of you.
Thank you, Dr.
Ustaz,
Ali.
Dr. Dina. Assalamualaikum warahmatullahi
Waalaikumsalam.
wabarakatuh.
Salam. Thank you, doctor.
Thank you, Doctor.
Welcome.
Thank you, Data.
Thank you.
Doctor.
Thank you, Doctor.
Thank you.